Okay. Good. Yeah. Okay. So thank you very much for the opportunity. I have to get this here sorted to talk here. It's a great pleasure. Now, and I will present some work that we are doing in Stuttgart on Rydberg atoms and tweezers. And we'll talk about a new project that we have set up in the last 3.5 years that aims to use so-called circular Rydberg atoms for quantum simulation. That's a really tough one. Yeah. Let's okay. It's fun. Okay. Yeah. So this is that's a project that works with strontium atoms and tweezers. And we are aiming to build a quantum simulator with these new types of Rydberg states. And today I would like to show you a few results, a few first results from that project. Before that, let me start putting this into context. Given the experiments that we have in Stuttgart at the Fifth Institute of Physics, that's the Institute of Professor Pau. So we basically have 3 cold atom experiments that machines that work with Rydberg atoms in various contexts. The first one is a rubidium gas experiment that is focused to study impurities, ionic impurities, Rydberg impurities in degenerate gases, and that hosts a very special device, so-called ion microscope, that allows us to image Rydberg atoms and ions with very high resolution and very fast temporal resolution as well. The project that I'm going to present today is a tweezer experiment that is working with circular states in optical tracks. And then we have recently also started a quantum computing project where we aim to implement a new type of qubit in the strontium system. And if time allows, I will flash a few slides about this. So let me motivate this work with circular atoms at the beginning. So the platform that we are using, I think I don't have to introduce this much, is the tweezer platform that has been really shown fascinating results in the last 5 to 10 years in the context of quantum simulation and quantum computing, mainly coming from its large tunability when it comes to the geometry that you can arrange your atoms, but also the dimensionality, and this can be nowadays done with thousands of qubits in these systems. And if you want to use now Rydberg states to let these atoms interact over micrometer distances, then you're typically faced by a strong limitation that is the lifetime of the Rydberg state itself that actually sets a limit for the coherence time of this setup. And so the aim or the goal to use these so-called circular Rydberg states is to actually improve on this fundamental issue and provide this platform with lifetimes, coherence times that are orders of magnitude larger than what is currently possible. Then we want to use this, scale it up to large atom numbers to basically to implement a spin model. Many body physics. So for those of you who are not so familiar with Rydberg physics, I have to introduce a little bit what a circular Rydberg state actually is and why this helps to push the lifetime of this platform. So the standard approach to, let's say, implement a spin or a qubit in this platform is that you encode this in, let's say, the ground state of your atom and the S state, or in the alkaline earth atoms can be also p states, metastellar p states, and then you connect this via 1 or 2 photon transitions to Rydberg states that are S states or P states or D states or very low angular momentum states, and this forms your qubit, and the Rydberg state gives you the interactions then between neighboring atoms in neighboring sites. But these Rydberg states are certainly prone to decay, so they live for a couple of tens of microseconds maybe, and when decay happens, then certainly the coherence is over, and your quantum simulation will face dissipation. And so these tens of microseconds actually then set the time scale that you can typically run such a simulation experiment. One way to actually improve on this is you want to use maybe Rydberg states that live considerably longer, and the circular states are such Rydberg states that live very long. And so what are circular states? Circular states are now states for a given manifold, a given principal quantum number n, where you maximize the angular momentum of the electron. And so for, let's say, some principal quantum number n, that means that the angular momentum quantum number m and its projection ml is maximized. So if you would draw the orbit of such a Rydberg electron, it's really a core-type planetary orbit. It really looks like a circle around core. That's why it's given this name as circular Rydberg. And the nice thing now about this is because you have put so much angular momentum into the electron, is that the state simply cannot decay anymore optically to the ground state by emitting one or two photons into selection rules. And that allows to achieve lifetimes for a Rydberg state that are really orders of magnitude longer, pushing them from the tens of microseconds into the tens of milliseconds. That's the goal of this project, to use them these long lifetimes. Okay. Circular states are not new on the table of atomic physics. They have actually been the working horse for the beautiful experiments by the group of Serge Roche on single atoms in microwave cavities, or the Nobel Prize winning research with control of single photons and single atoms in interaction. And if you follow this work, then you will recognize that when you work with these types of states and you want to make them long-lived, experiments typically work in a cryostat. The reason for this is that although optical decay of these circular states is forbidden by selection rules, there is blackbody photons around that would actually bring you from a circular state of a certain principal quantum number n to neighboring manifold n plus minus. And to get rid of these blackbody photons, you have to bring the whole machine to cold temperatures and basically work in a cryogenic environment. And there's Endeavor in Paris along that route that also building quantum simulators with circular states required. So we have tried to go a different route and doing that with strontium. And the idea is actually to build an experiment that would work completely at room temperature without any need to do cryogenics. And the idea is pretty simple. Yeah? So if you have your atom now, and you would place this atom inside a capacitor structure, yeah? Inside two metal plates, two parallel metal plates, and you can actually basically suppress the decay of these atoms due to microwave decay or due to blackbody radiation, simply because the wavelengths of this radiation, microwave photons, are typically in the millimeter and centimeter range. And now if these plates of your capacitor are actually closer together, yeah, than the half of the wavelengths of this radiation, and you basically cut the blackbody spectrum from below. There's a certain cutoff that you provide by these plates, and you simply don't let these modes propagate and dissipate. By this, you can, so to say, switch off blackbody radiation up to a certain wavelength, and if you engineer this capacitor the right way, then this allows you to basically suppress the blackbody decay of these circular states in a room temperature setup without any cryogenic cooling. That's how this looks like experimentally. So that's a sketch of our experimental setup. It's a standard glass cell in which we can prepare a magneto quantum atoms and load in the laser arrays. But the core of this experiment is really this electrode structure here inside that consists of electrodes that are just there to control electric fields in the setup, to control the Rydberg states themselves. But what you see here are these bluish plates, and those form actually this suppresses black body radiation. And these plates are made not from metal also, they are made from glass and are coated on the inside with a layer of indium oxide, which is a material that is highly conductive and therefore highly reflective in the microwave domain, but is transmitted in an optical frequency. So basically, you build an electrode or you build a microwave cavity that you can look through. And that's useful because at the same time, as you want to suppress the black body radiation, but also you want to bring your tweezer light in or your optical filter. Something where it can shine through the black. This ITO cavity is basically. Okay. Yeah, I said we do. Yeah. No, you can do it with in the alkali. The reason why we are using quantum is now. Yeah. So the reason why we picked quantum for this experiment is it's an alkaline earth atom. It's structured very similar to what we heard before for ytterbium. That means when you have one of your electrons in the Rydberg state, and the second electron back, that's optically active, basically quantum plus ionic core that has optical transitions that you can use. And you can use them now to, for example, trap your circular states, trap your Rydberg atoms in the tweezer. You can use it to rest on the Rydberg atom and actually detect it optically. You can also think about using this for optical manipulation of the Rydberg state itself, and I will show you an example at the end of the talk. And so basically, this gives you a system where you have your very distant electron in the circular orbit that you can control by a microwave field, for example, implement a qubit between two circular states. And at the same time, you have an optically active ionic core that has clock transitions, strong cyclic transitions, and you can even think about implementing some interaction between these two electrons that you can use for state manipulation. Okay, this is a picture of our tweezer array. For the moment, it's a small array. We have about 10 to 30 atoms in there, depending on what we want to do. And this is done at a wavelength in the visible range, for the reason that at this wavelength, the circular states will actually be trapped in the tweezer in a bit. That is data that shows that we have single atoms under control in the system. That's a typical histogram of optical photons that we scatter from individual quantum atoms, as we have also seen in the previous talk, where we can actually distinguish 0 atoms in a trap from 1 atom in a trap. We can rearrange the atoms, and we can also pull them very well to their state. These arrays intercombination language. Okay, then once we have control of the atoms in the trap, we want to bring them now to the circular electrode, to the circular orbit, and this is a bit involved, so I have to actually bore you a little bit with that physics, how to do that. Because the reason, I mean, the nice property of these circular states that they have long lifetimes actually comes with the fact that there is not much room to control them optically. They don't talk to any optical photons, they only talk to microwave photons strongly, so you have to have some means that are non-optical to bring them into this circular state. And you do that by the following trick. So you start with an optical excitation of a Rydberg state that already has some sort of large angular momentum, so that you have a very small quantum defect, and that Rydberg state is actually close to the degenerate state of degenerate manifold of IL states, and in our case, this is an F state. So we optically excite in that specific experiment now to a 79 F state. And this has only a quantum defect of around 1 gigahertz to the hypergenic manifold. And if you put this Rydberg atom now into an electric field, then you see the linear Stark fan of high L states that splits up in the electric field. Three photons in the zone, but go only by a single, not by. So you bring this atom now into an electric field, and then you see that this F state actually smoothly attaches to a ladder of states that are all equidistantly split by the Stark. And the circular state is actually the one that has the lowest Stark shift. It's actually only shifting quadratically in the electric field. And is sitting there in the middle. And so now you have to bring, the name of the game is now you have to bring your electron from here, from this elongated F state, that is polarized F state in an electric field, up to the circular state by actually bringing in this case, 76 quantum angular momentum into the water. And you can do that by radio frequency, because this ladder of states here is equally spaced. You only need one radio frequency here that is resonant with this spacing here. And then you can basically drive the system from this stretched F state to this here. And so you can imagine that this is called radio frequency adiabatic passage. Has also been explored long ago in atomic beam experiments. But you can think of it as the follows. So by actually dressing this manifold here with your radio frequency photons, you actually build a kind of giant crossing, multi-level crossing. And the ground state of this system is actually a state that is to the left-hand side of the crossing is the F state, whereas to the right-hand side is the circular state. And if you open now, crank up the radio frequency right now, you can actually make that crossing in the voided crossing, actually basically, and scanning the electric field across this resonance and bring the F state coherently into the circular state. For this, you need very good control of these radio frequency fields in the setup, because what is actually important is that the polarization of this radio frequency field is very nicely circular. And that explains also the structure of these electrodes that we are having here. If you would look onto this capacitor or this electrode structure from top, you would see that we have a ring of 4 electrodes that is actually sitting on a circle. And then by applying voltages that are 90 degrees phase shifted, we make a very nice circular radio frequency field. And then exploit the very good electric field control that we have in the setup to actually bring the electron coherently. To test the level of control that we have in these experiments on the electric field, I just want to flash a few measurements of the Stark effect of this initial 76 F state, so that's the typical parabola of the state in an electric field. We apply voltages to our electrodes, and just to see how good we are, we just went up on the principal quantum number and we went up to a state that is quantum number 200. But that's a big effect. The orbit of this atom is 8 miles. So the electron actually reaches into the next field. And this requires a field stability that is well below a millivolt per centimeter of the days and weeks. Okay. Well, now once you have this F state, you implement this radio frequency adiabatic passage, and then you bring your electron to the circular state. And now you have to implement a qubit or spin up, spin down system to actually use this for quantum simulation. And the way we have encoded the first qubit now in the system is we are using 2 circular states of n equals 77 and n equals 79 that we connect via 2 microwave photons and drive in 2 photon microwave transitions between these states. And the way we detect them now, so we have to also somehow detect which Woodland states we are. We do this via field ionization and ion detection on an ion detector that sits inside the chamber. And then we can detect such traces here. These are basically counts on an ion detector as a function of the ionization field, and this allows selective detection of Rydberg states. For example, this is signal that comes from the initial F state. This is signal that comes now from the circular state, specifically 79 and 77 circular state, slightly different electric fields, and you see that we can nicely distinguish them by the ionization field. Applying now this microwave drive here between these two adjacent circular states, we can write Rabi oscillations, for example. This is a Rabi plotting on this two-photon microwave transition that starts in the 97 circular state and is then coherently populating 77 back into a couple of tens of microseconds, and there's decay on this, basically from small power fluctuations on the microwave line that we send in. But this allows you then, for example, to occupy also a superposition state of two circular states, 2n apart. And if you would plot the orbit of such a state, it would actually be a circular orbit again, but nodes, that's a neutral direction, two nodes, would actually form a dipole that rotates around. Okay, that shows you that we have coherent control over these circular states, and we wanted to investigate now how long we can keep this qubit coherent by doing the Ramsey spectroscopy. That's shown here. So that's now not a Rabi signal, but a Ramsey signal. We're basically preparing the superposition of two circular states by a two-pulse rate for a certain time and closed into per by a second by measure the population. And so then we can see nice Ramsey fringes, and we see a decay, and we can actually then characterize the coherence time of the system by performing also spin echo. That's the red data here, putting in a pipe pulse and echo out of some of the phasing that we see, and this allows us to pinpoint the T2 time of the system, including spin echo, to a few hundred microseconds. This already is something that is the longer coherence time that you would actually have at a lifetime of the escalators, so to be short coherence time now. And we exactly know why the qubit dephases. This has to do with the residual magnetic and electric magnetic field noise that is on the order of milligauss in our setup, and electric field. Okay, we can also measure the lifetime of the circular state now by basically looking on our ion traces here and counting how often the state actually goes to a window here in the detection that would not be attributed anymore to the initial circular state. Circular state with one principal quantum number less. And by then evaluating such ionization traces as a function of time, we can actually plot the lifetime of the circular state. And extract the T1 time, that qubit, which for this 79 circular state we have analyzed to be. Okay. Interestingly, if we go to the 77 circular state, we find a lifetime that is significantly shorter, not in the above millisecond range, but more hundreds of microseconds, about 200 microseconds or so. And this is exactly the capacitor that is active. Plot now the lifetime as a function of principal quantum number, we would really expect this steep rise of the lifetime at a certain principal quantum number where the black body field is going to be suppressed into the set distance of our plate. So the plate capacitor is actually expected to act at around n equals 80. And if we would go higher in the principal quantum number, we believe that we can reach, hopefully, lifetimes that are going towards the 10 millisecond range. And I would really like to point out that this is a competitive with no climate. Okay, I would like to spend the last 5 minutes to talk a little bit what you can do now with this Schronzel cluster. We have now this Rückberg electron in the circular state, but I told you we have an optically active core now, strontium plus ion, that you can use for manipulation of the state. And the first thing that one can use, that one can make use of, is that this core has a polarizability, and you can use it for tracking. Typically, if you have an alkali Rückberg atom in the tweezer, this atom is escaping from the track. There's no force that binds it, but only quantum force that actually kicks it out of the thread. We can now counteract this quantum force by using the co-polarizability of the strontium plus ion, and by that keeping the Rückberg atom trapped. And we really want to have that atom pinned if you want to exploit these milliseconds lifetimes for quantum simulation. You want to keep the atom in the track, and we can actually characterize the trap depths by measuring differential level shift of this circular qubit in the microwave transition as a function. These are depths and actually try to characterize the trapping. Okay, this is yeah. For this, you're actually using just the polarizability of this core. The question is now, can you do more with this? And the nice thing is that you can also resonate it, really using transitions in this core in resonant fashion. That is very special to the circular state. If you have an S state, for example, of an alkaline earth atom, and you would excite the core, then the S state would penetrate to this second electron that you excite, and they can collide, and that leads to a process which is called autoionization. That's a very rapid process which typically happens in the 100 picosecond time scale. So all you can do when you resonantly excite the core for an S state is you can make an ion, not much more. For a circular state, the electron never comes back to it. And that's why this autoionization process is basically completely switched off, and you can really drive on these inner core transitions. That's an example, where you see this. If you drive, for example, this 422 nanometer line of the strontium plus ion in the presence of a low angular momentum Rückberg state, and you just get a large, like a huge line width, 2 gigahertz, which indicates this autoionization. To do that with a circular state, you basically get the natural line width back, which tells you that there's no detrimental process. So the fact that you can optically drive these inner core transitions opens questions like, can you maybe sense some tiny interaction between these two electrons, although they never meet each other? And you can do that by bringing this strontium plus core to a D level. So all these some of these alkaline-like ions, metastable D states, like calcium. Quantum also has this. You can shelf your population into this metastable D state, and this D state has a quadrupole moment. And this quadrupole moment can now interact with this circle, with the Coulomb field of your circular electron that is far apart. This gives rise to a little level shift on the circular orbit of tens of kilohertz, and you can use this. Try to measure it. I have to be very quick, I think it's 1 minute or so. In principle, what you can do is you can sense now this level shift on the circular orbit. It actually also depends on the MJ quantum number in which you come. It can be a redshift or a blue shift. And we can explore this in our Ramsey interferometer by looking at shifts of the Ramsey fringes in spin echo. And read, but this, you measure these Ramsey fringes, the presence of this quadrupole interaction. You can actually determine its interaction strength, which we find to be in the few units. So you can use now this tiny interaction between these two electrons to optically manipulate the circular electron out there by playing with inner core transition. This is data showing that the Ramsey fringe in the presence of this interaction and how we expect actually the strength of the interaction by some heat mechanism. Okay, with this, I'm actually at the end. I would like to thank the team working on this setup, specifically this person here, who was my first PhD student when we started 3.5 years ago. He just graduated now 2 months ago. Christian Hölzwitz, the best great work. We've got lots of fun with them in the lab. Meanwhile, the team is a little bit bigger, and we're just on the start. We want to use now these circular capitalism to build up large arrays to measure their pair interactions. Kept on fighting.
Thank you, Florian, for that. So, sure, there. Technical question. You have another place to cheat against decay of microwaves. Don't they also cheat?
Yeah.
Put it in?
Yeah. So I mean, Woodbury atoms are very sensitive to microwaves, so we just kind of your microwave.
Okay.
Yeah. So, I mean, this adiabatic technique that I showed you is really the simplest, almost the simplest thing. There's more complicated sequences where you add some optimal control techniques to your active field or frequency bands during the lecture that allow you to go higher. Because it's really clear where this comes from. This infidelity actually comes from the fact that this letter state, you go to the F, what the F state becomes a little distorted. This you have to. Then we can go, I mean, there's work on the couple in Berlin, and the first reflection showing 99.
For the integration, question for people this
This is so it depends. It's more from more than 95%. But I think also this can be. So basically, it's a little bit of you have to be able to really distinguish the background from other states in the ionization traces. But I believe that right now the can be put beyond. On the microwave generator, it's a 2 milliwatts, what drives and then you have typical lifetimes that we would get better, but also this I can show now fascinating paper by now. Who have seen like really years you don't have it for this. So we have measured a few couple of seconds. This is not like and we have to investigate a little more what comes from the electrode. That should be a lot of stuff. One also has to keep in mind certainly the experiment with the taking here will be minute or so.
Okay, thank you very much again for the talk. The last speaker of our session, which is Pietro Brighi, and he's going to talk about non-reciprocal dynamics and non-Hermitian skin effect of repulsive and bound pairs.